Good morning. Any questions about anything before we get rolling on the material for today? Question is, when will Bit Basher grades come out? Well, you already know what it is because the thing was self-scoring, and so when you ran the whatever the heck it was called, driver program, you got your score. So I will put those out on Canvas by running a script that I have that goes to and essentially runs a driver for everybody's stuff. But you already know what the numbers are. But what I'll do is, I since we've got some scores behind us now, the first exam and the first project, and some homeworks have been graded. I will take all that and I'll run a k-means clustering algorithm on it, and I'll show you the distribution, and you can find where you're at in the class, and then you can see what cluster you fall in the clustering algorithm. So I will run that tonight, probably have it up on the Canvas site tomorrow at some point, and so then you can uh, see where you're at, how you're coming, at least with all the bets that are on the table so far. How do you show your work for the GDB in general? I don't understand the question. What do you mean GDB in general? How do you show your work for GDB in general? What do you mean show your work for GDB? Project two, when you run the program from within GDB or however you run it on Schofield, contacts a grading server, which keeps track of how many explosions you've had and how many phases you've diffused, and builds a real-time scoreboard with all those results in it. You're thinking about project one that says show your solutions. That's project one you're thinking about, not project two. Project two, you're just either blowing up the bomb or you're diffusing it, and it automatically, magically contacts my grading server that's running over there in Schofield and keeps track of all those things you've diffused and all the times you've blown it up. So that's all there is to be done. It does it itself. It's magic, right? Are you referring to some rubric that is associated with the Canvas page thing out there? Yeah, I think that's something that one of the TAs must have stuck out there one term. I need to go in and delete some of that crap. Um, yeah, so some rubric that got stuck out there on Canvas, just ignore that. That's some nonsense, some TA stuck out there at some point that doesn't mean anything that I need to get rid of. Um, and what else was there? Something about the curve of the midterm. Well, there is no curve. The way it works is we do these things and you get a number, you get a score. And so everybody accumulates all these scores, and each of the categories like projects, homeworks, exams, whatever, they have a weight, that was specified in the syllabus as to what the total weight of that category is. And if you add all those weights up at the end of the term for those categories, you get 100. So it's, a score out of 100 eventually by virtue of those weights. But for each individual assignment, there's no quote curve. I don't really like using that word because students use that word incorrectly 99.9% of the time. It's a curve. But anyway, the individual product scores that you're getting on these individual things, we don't do anything to those other than run them through a weighting formula, and then you get a number, right, for whatever your number is versus somebody else's number. And we take all those numbers and we add them all up, the weights, and then you get a um, distribution. And then I run a k-means clustering algorithm against that score, which I'll publish, hopefully tonight or tomorrow. You'll see the distribution of all the scores that have happened so far, anonymous, of course, and then you'll see the results of the clustering algorithm, see what cluster you're falling in. And so really, that's the most important thing, is what cluster are you placing in the scores that you've been able to post for the assignments that we've had up to this point. So hopefully after I publish the distribution and the clustering algorithm, it'll be a little clearer, and you'll see how you're doing versus everybody else in the class and everything. No, there's no such thing as a bell curve. It's a k-means clustering algorithm, which I think I explained a little in the syllabus what that is, but at some point we can discuss further what k-means clustering does. It's a much better, more realistic, sophisticated, accurate mathematical way of grouping scores into groups that belong together. So we can talk about that at some point if you want, but I'll show you the results of all this and get it posted up there. So let's move on to the material that we need to cover today. And first thing we need to look at is some stuff that sort of comes from the homework you turned in Friday. One of those problems, I think it was 367. That was the last problem. I don't know. Was kind of some kind of interesting stuff going on in there, and I wanted to make sure you understood what they were trying to make you realize by working that problem. You've seen that in C, in the Intel architecture, C calling conventions, that we have this idea that we pass the return result of a function back from the function to the caller by leaving it in the A register. So if we had a short, we, expect to see it in AX. If we had an int, it would be in EAX. We had a long, we'd see it in RAX, etc. So the A register is the register is just designated to hold the return coming back out of a function being given to the caller by the callee. Well, what if you want to hand back something that won't fit in a register, like maybe a structure or an array or some non-scalar thing, in other words? How do you do that? Well, of course, the answer is you hand back a pointer to the structure or a pointer to the array. But the piece of the puzzle that you have to fill in, you may not have thought through, is where in memory does that structure or array live that you're, quote, handing back, returning to the caller? Well, it can't live in the activation record of the callee because that just disappears right after we um, finish the call. It conceptually, retracting the stack and all that, those local variables and things that were in the callee are supposed to go away. So it can't live there. So where does it live? Well, actually, it lives in the activation record of the caller. But then how does the callee know where to put it? Well, the caller hands an address to the callee saying, hey, this structure that I want you to return to me, put it in my activation record in some space that I've reserved at this address. So that's kind of a hidden parameter that's being passed into the callee that isn't something you see listed in the C code as the list of parameters that are there. So I have a little sample program sitting here, and we have this function called foo, and just like in the problem that you worked, it has a STRA, which is this type def struct, 3 longs, or 2 longs and a pointer to a long, actually. So this thing takes up 24 bytes, right? That ain't gonna fit in a register. So how does foo return a struct A back to somebody that calls him? Well, if you look at the code over here for the call to foo, you see this 7 being passed in to the foo function, and that is going into um, the ESI register. So the 7 is the L1, which is got the value 7 put in it down here in main. We look in main. Come on, get up there. In main, you see we got a 7 that we're putting in this LM1 variable, and then we're handing the LM1 variable to foo. So that's the first parameter. But hold the phone, wait a minute. 7 is going into ESI, which is where we would expect the second parameter to be, not the first. Similarly, LM2 has an 8 in it. We're handing it there, and you see he's taking this 8 and putting it in EDX, where we would expect the third parameter to be in that register, right? And then we're taking the address of this LM1 variable, and we're putting it into LMP because he's a pointer to a long. And that's the third parameter. So we see that happening over here, where we're getting the load effective address of 8 past where the RSP is pointing, put it in RCX. So that's getting the address of the LM1 variable out of the activation record of main, sticking it in what we'd expect the fourth parameter to be, 2, 3, 4. But they're 1, 2, 3 code. So why are they 2, 3, 4? Well, because the first parameter, what RDI has in it, is actually that hidden parameter, that address of a location in the caller where he's reserved some space to hold the struct that the callee is supposed to return. So he's handing him this address, and then up in foo up here, when foo is actually stuffing things into this return deal, right? He's actually using that hidden parameter to put it in the activation record of the caller. So you have to realize that when you have a non-scalar return, like returning a function, struct or an array or something that doesn't fit in a register, anything that's non-scalar, right? The caller has to reserve some space to hold that result in his activation record and then hand the callee the address of that so the callee can reach up into the caller's activation record and deposit that non-scalar that's being returned. So that's a little tricky, right? The callee, the guy that's generating the return, doesn't have the space for the thing being returned, but the caller reserved the space for it to be returned. So hopefully you see this hidden parameter business going on with a non-scalar return, see how that is implemented in the calling convention. The problem they gave you had that hidden parameter being passed in, but it was a little even trickier than that because if you looked at the C code, it had one parameter being passed in, and they were only passing in the assembly code one parameter, the hidden parameter, to the pointer to the location for the for the structure to be deposited in the caller's activation record. But you never saw the actual one listed in the C code being passed, and that's because the compiler optimized it away and was simply reaching back up the stack into the caller's activation record to get the parameter rather than actually passing it in to a register. So there was a sort of two things going on there. Figure out how you return a non-scalar and also catch the trick that the compiler optimized the actual parameter you see in the C code away by reaching back up the stack rather than passing it through a register. So that was a little tricky, that problem, right? But hopefully it forced you to think about how in the world can you return something that won't fit in a register as a result of the function, right? So are there any questions about how that's accomplished in the calling conventions? Well, if not, we have some loose ends to attend to from lecture 13 that we stopped and did not go into because they didn't appear on the exam, and we wanted to devote the time before the exam to pounding on things that were going to be on the exam. So now we need to go back and finish up these ends from lecture 13 and some issues about arrays. And it's good that we do it in conjunction with what I just showed you about returning a non-scalar, because this is also concerning how do we pass non-scalar things into functions. We just talked about how do we return non-scalar things out of functions. And now we want to talk about, well, wait a minute, what if I pass an array into a function? Well, in C, everything is passed by value, but we don't take a whole copy of like an array and make a copy of it, pass it down somehow into the call E. We just pass the address. So everything that gets passed in or out can fit in a register, right? If we pass an array or we pass a struct, we're actually passing an address of the array or the address of a struct, right? Does that make sense? So non-scalars are always passed as an address to the location in memory where the thing actually lives. So we go back and look at this little example we had with our zip dig. And if you remember, a zip dig was an array of five integers, right? That was a type we created called zip dig. And then we created this two-dimensional array by saying, let's have four of those one-dimensional arrays. And we got this two-dimensional array guy, and he looks like this. One contiguous chunk of memory right after each other, each array, which you can think of as a row in a two-dimensional sense, row column kind of thing, right? So we got five of these arrays, I'm sorry, four of these arrays of five integers, right? Two-dimensional guy. And we saw how we computed these indices into the add into the array at the right addresses to jump over the right number of rows and then go to the column element within the row, and how we computed up that address to get it. And we noted it was laid out in row major order. Well, it turns out there's a little tricky thing going on in C. This is showing where we computed the offset to get to some element within the two-dimensional array, right? Remember that? But if we have this declaration, which is different from the one we just looked at, this is saying, okay, I got one of these zip dig things, an array of five integers. I'm going to call it CMU. I got another one called MIT, another one called UCB. And I'm initializing them with these aggregates. And remember, there's no guarantee when you make these separate variable declarations like that, that they actually live right next to each other in memory. And you can't assume that they do, right? Compiler can put them wherever he wants. It doesn't guarantee that they're adjacent, like in the case of our two-dimensional array up there, it is guaranteed that they're all adjacent, right? Because that's one declaration of a two-dimensional array. This is three declarations of one-dimensional arrays, right? Well, now we turn around and we say, okay, we're going to have this other array called university, and it's going to be U count 3 big. And what it is an array of pointers to integers. And what are we initializing it to? Well, here's our aggregate. It's got three things in it. When you write the name of an array down in C, what does it mean? It means the address where that array begins. I didn't give it any subscripts. I'm not trying to get an element out of the array. I'm just talking about the array itself. So that's the address where that array begins. So these are three addresses of these three variables, which are arrays of 5 integers. I'm putting those addresses in this array, pointer to integer. So it looks like the picture here. There's university. It's got three things in it. Each of them is a pointer to an integer. And in C, you just have to kind of get used to this idea about, well, pointer to how many integers? Well, however many you want to pretend it is, right? There's the no, another one of the sort of dangerous no training wheels kind of aspects of C. The size of this thing, however many integers it is, isn't really included in this concept here. You just walk across it however you want to do it, right? So pointer to integer is like same thing as array of integers in our C mindset, right? So here we have pointer to integer. It's pointing off to this array of these integers. But this is different the way it's laid out in memory from that contiguous two-dimensional array that we saw. These things could be any old locations in the world in memory, and this is still going to do it. I'm going to go in here and get this pointer, and then dereference the pointer, and then subscript and off the beginning of that to get to the element that I want. So it's kind of a different flavor, if you will, of two-dimensional arrays. It's not a real two-dimensional array. It's an array of pointers to arrays, right? So the fact that we're trying to mush these arrays and pointer concepts together in C is now possibly getting a little confusing. So you have to watch how the thing was declared, right? To know what it is you're going to get. Well, the other confusing part about this is if you look at the code to access that thing that we just looked at, it looks completely identical to the way you would write this code down to access the actual contiguous two-dimensional flavor of array. I've got this array and I give it an index and I give it another index. But the code that comes out of the compiler to actually access it is totally different from the code that would come out of the compiler if this was a contiguous block of memory computing up an index. So let's look at the code. It's 32-bit style code. Go 8 back off the base pointer gets us to the first parameter, the index, which we're conceiving of as the index into that university array of 3 pointers, right? So we get the beginning address of the university array. We multiply 4 times that index, and it's 4 because it's 32-bit computer, 4-byte addresses, right? So that gets us subscripting down into that array of pointers to integers to the right one, right? And now what do? We pick up a pointer there out of that array, put it in EDX, and now we go get the second parameter, the dig, at 12 back, right? And we use it to say, okay, I've got the beginning of an array, a zip dig array, 5 integers now sitting in EDX because I picked up the pointer to it out of the university array. Take that address and then multiply the second index times 4 because they're integers, jump over the right number of bytes, 4 per integer, move that into EAX, and now I dereference that because it's a move instruction, right? That's the parens. Generate this address, go to that address, get the value, put it in here. And that's how you return the int from the function, dumping it into the EAX register. So this goes and gets the individual integer we're trying to get, but the way it got it was different, right? It went into this array, got the pointer, then went to there, and then went off here and picked up the one that you're after. That's not the same as the code that we would have to if this was all one contiguous block of memory, like in the true two-dimensional array thing, right? How we would compute jumping over the right number of rows and going to the element in the column within the row. Do you see how that's different? So you have to watch how the thing is declared because when you look at accessing it, it looks completely identical to the other flavor where we had the true contiguous block of memory. That's somewhat confusing that it looks completely the same. And it's a result of this attempt to take the concept of a pointer and the concept of an array and kind of mush them together into one uniform idea, and then do pointer arithmetic and that sort of thing, right? Versus subscripting. So this is another side effect of that, or another consequence of that way of thinking, a way C thinks about arrays and pointers. Questions about this? We use this kind of thing all the time. Later on, we'll see where we can get dynamically allocated storage out of the heap, right? And we'll go grab a chunk of space out of the heap and another chunk of space, and we'll take the pointer to those things and we maybe stick those in arrays or something. And then we can just pretend it's accessed like a two-dimensional array to get to those, even though we grab these individual things piecemeal out of the heap, maybe. So we use this kind of thing a lot in C, and it's a little slippery when you first start looking at it, but think it through. Have an array of pointers, essentially, to arrays, right? Versus a contiguous chunk of memory where I've declared this thing to be an array of these arrays, these zip dig arrays, right? I have an array of these arrays. And that's a contiguous one, right? Whereas here, wherever the heck it went, I have an array of pointers to ints, and then I put the beginning addresses of those arrays in there as those pointers. It's different, right? Accessing it looks completely the same. The code for that access is different depending upon which flavor of array it was, the contiguous one or the array of pointers to arrays. Any questions about that before we go on? So the next little, yeah, here's the picture comparing the two. You declared it this way, the previous slides up there, we declared this one as the contiguous one, and there it is laying in memory. And we're computing based upon jumping over the right number of rows and then the element within the row. Whereas here, we declared it as the array of pointers to ints, and those were arrays themselves. That looks just like that, doesn't it? Two subscripts hanging off of something there. But this is the way this one's laid out in memory, and the code to get it is different from the code to get into this one. So hopefully it doesn't confuse you that this looks exactly that, even though they're different things. Questions before we go on? So another detail that we need to attend to, back to this business of how do we move non-scalar things around? Well, we're obviously passing addresses, right? When you pass an array into a function as a parameter, you're not picking up the whole contents of that array somehow and plopping it somewhere else in memory. You're just passing an address that points to where the array is already sitting in memory somewhere, right? And then the function that you're handing it to uses that address to go reach in and get to that array, right? So the question comes up, what happens when we want to have an array that doesn't have fixed size parameters known at compile time? So we'll look at some examples of that. The first one we look at has fixed size arrays. We got a define of N16, which is just a preprocessor textual substitution of everywhere you see this capital N, stick 16 in there before the compiler ever sees it, right? Now we have this type def, little type def of a thing called fixed matrix, which is a array n by n of integers, right? So there's our contiguous two-dimensional array of fixed bounds known at compile time, right? And then we have a little silly function that you pass it the array, which is an address, right? And these two integers, which is the row and the column indices, and then we're going to access it and return the result back, right? So then what if I wanted to have the one like on the bottom here? I want to have an array n by n, but I don't know what n is at compile time. I'm going to pass n in as a parameter and then use that parameter to declare what the size of this other parameter is. And then I have my indices for the row and the column that I want to access, right? So this is not a fixed size. It's a variable dimension array, right? How does the compiler emit code for that versus if it knows at compile time what the size of the bounds are? Well, that's a different issue. In fact, the matter is that in C, you used to not be able to do this one on the bottom here. You couldn't use this variable as in another declaration of another parameter. It wouldn't let you do that, nor could you have a local variable that was declared to be an a n by n based on what that parameter that got passed in. You couldn't directly use it in that fashion to say this is a variable size thing. C99 and beyond, they let you do this now, right? And we'll look at the code that comes out of the compiler to do that. And in the old days, since they didn't let you do that, we had this trick for how we did it that involves using a macro. And we'll look at that alternative way of doing this. But we'll put that off for a few minutes and come back to it. First thing we want to look at is, well, if I know the dimension of the array at compile time, what kind of code would I generate? Well, I can do some optimization. If I know what the bounds of the array are at compile time, I can go ahead and do some arithmetic that doesn't have to be done every time you run the program over and over again at execution time. I just do it once at compile time, build it into the code because I know the sizes at compile time. So the code could look something like this, 32-bit style stuff, right? 12 back off the EBP is the second parameter. That's this index I, picking that up, right? Now what I'm doing, shift arithmetic left long word 6, so that's 2 to the 6th, 64, times what's in EDX. So now I've taken I and multiplied it by 64. Well, what the heck is I and what the heck is 64? I is supposed to be my row index. So whatever I is, I need to jump over that many rows to get to the right row and then apply the J subscript, right? What's the size of a row? Well, the size of the row is the number of columns that you have in your matrix, right? What is that? Well, I know what it is. It's 16. It's a fixed thing that was declared right there in the program at compile time. So what are the element sizes? Well, they're integers. They're 4 bytes big. So 4 times 16 is 64. So this is saying take the row index and multiply it by 64, and that tells you how many bytes to hop over to jump past the appropriate number of rows, right? And now I get the third parameter, 8, 12, 16 back off BP, right? Put it in here, so that's the J. And now I'm shifting it left 2, so that's multiplying by 4, 4 because an integer takes up 4 bytes. So the column index has to be multiplied by the element size of each element in the array, right? So now I'm jumping over the right number of bytes to get within the row that I'm accessing the right column. position, right? So now I take the beginning address of the array, right, which is my first parameter. He's 8 back off of the base pointer. And I want to add to it this EAX, which is the J times 4 thing, right? So now I've got the beginning address of the array plus J times 4, and my formula for indexing into the array, right, this business here, up there, says take the A plus J times 4 and add, jumping over the right number of columns, and now you will be at the right address. Since it's a move, the parens mean go to that address, pick up the value that's there and stuff it in here, which is the EAX register, which is how I return something from the function. So there I've reached in and got the right integer, 4 bytes, long word, out of the array, jumping over this many rows and jumping over that many integers within the row, the column index, right, off the beginning address of the array. But the point being, the compiler could pre-compute at compile time this 64 business here, right? Because he knows the size of a row is 16 integers, right? So he just crammed that into the code here, it pre-computed it. But what if I have this flavor? I pass n in as a parameter, and now I'm using that n in another parameter to declare this to be an array of n by n. What's going to come in here is, of course, an address for the beginning of this array. It's a non-scalar. You always pass an address, right? And then here's the row and the column index, I and a j. And now we reach in there and get it. But how does it generate code for that? It doesn't know what n is at compile time, so it can't pre-compute that 64 thing. So what's going on? Oh, well, here we're getting the beginning address of the array, 8 back. Oh, we're getting the n, rather, 8 back. And now we're saying multiply n times 4, because they're integers. That's where that 4 comes from. And now I want to put that into the EDX register. And then I have an actual multiply instruction. Multiplying 16 back off the base pointer is what? 8, 12, 16. That's my I. I'm multiplying I times n times 4, right? The row subscript times the number of elements that are in a column in times 4. So what is that representing? The number of bytes to jump over I rows, right? But before I had 64 times I. I didn't have to do this multiply the thing, right, at execution time. And now it takes the J, 20, 8, 12, 16, 20 back, J, pick it up, put it in EAX, now shift it to multiply it by 4, jump over integers, right? That many integers. And then add 12 back, the beginning address of the array, to this EAX, and then go in and get EAX added to EDX, the jump over the number of rows or whatever, and we jumped over the number of integers within the column. So we dereference that, pick it up, put it in there. So we've gotten the element out. Some of it looks the same, but we've got this multiply in there that we didn't have in this, because we pre-multiplied the thing at compile time, because we know what the fixed size of the array is, right? We don't have to do it at execution time. Multiply instructions, one of the most expensive things you can do in terms of the number of cycles it takes, right? He couldn't use a shift to fake it, right? Because he doesn't know what the heck n is. He doesn't know if it's a power of 2 or what, right? So we had to actually use a real multiply instruction. So the flexibility to have this function that we're writing be able to work on any n by n size array and have this code work to access an element in any n by n array I might pass in here, as long as I tell him what it is, cost me something in terms of time, right? The flexibility to do that is costing me some time at execution time for this expensive multiply instruction. Whereas if I knew at compile time what the bounds of the thing were, I could do it once at compile time, and at execution time, I don't have an expensive multiply instruction. I just have this cheap shift one cycle, knowing that it's 64, right? So that flexibility, that convenience, if you will, generality, abstraction, whatever you want to call it, has a cost at execution time. This is a theme that you will see repeated over and over and over again as you play with computers and concepts in high level languages. There's a tug of war going on between giving the programmer a high level abstraction, something that's a more general concept, and trying to make it run efficiently mapped onto the architecture of the computer. And the art and science of language design and compiler design live right on that knife edge, trying to go as far as we can with flexibility, but still be able to implement it efficiency. And then depending upon the target domain of the language, they may not care about efficiency. So, but there's this definite tug of war going on between high level abstraction and how fast you can run it on the computer. And you see that illustrated just in this example with this ability to have the variable sized array, which means I can write this one function, hand it 27 different flavors of n by n arrays, and this code will work. Whereas this handles one single thing, a 16 by 16 array of integers, right? It runs faster than the general case, right? Where we have to compute it up at execution time. So you see the difference, right? Both of them are ultimately just getting an address passed in for the start of the array, right? How we use it slightly different. So now we look at this other problem down a column in a two-dimensional array, right? Like get a column vector out of a matrix or something, right? So we have type def fixed matrix n by n, and we want to retrieve this column out of the matrix and return that column vector. I mean, not return it, but stuff the thing out of the array into that. So we get passed in the address of this array for the destination, the column vector, right? And we get passed in the address of the array that's got the two-dimensional array, and we get the column that we want, right? We got a little standard for loop, 0 less than n, the size of the thing, increment it, right? Go walk down the column, hold I fixed, vary j, which is walking down the column, right? Picking up each element and stuffing it in this column vector, right? So what's the code look like? Well, once again, I know the fixed size array at compile time. I know that to get from A in the array at this column in one row to go to the same column in the next row, how many bytes away is that? Well, I know what the size of this thing is at compile time. It's 64 bytes, once again, 16 times 4, right? So you'll see that being used right there in the compiler, spitting out code going, if I had the beginning column address, which is what this business is, right? I'm getting the beginning column address. The ECX has the beginning thing of the array in it, right? And then we're getting the EAX and putting it in EBX plus EDX times 4, right? That's saving it in the destination. Now I want to go to the next column. So I increment my loop counter and then I increment by 64 this address ECX to go to the next column, and it's 64 because I know it's a fixed size thing. So if I pick bytes, I'm going to the same column in the next row. So there's another thing that you can do in the compiler if you know the fixed size array at compile time that you couldn't do if you didn't have a fixed size array. You'd have to be computing up how far to jump to get to the same column in the same array because you don't know how many elements are in a column in the non-fixed case, right? So it would cost you more to walk that column computing those things up at compile time. So now I go back to the third one and look at this thing here. This is the way we used to have to do it before C99. And so you still will run into this kind of code and you should know how it works. Some people still use it even though you can do this kind of thing here because they like to grab the bull by the horns and do their low-level stuff themselves. This is a macro. You've seen pound define used to define a number like n is 16. This is defining a macro, which is kind of like an assembly language before we had high-level languages and we wanted to plug in the same chunk of assembly language over and over and over again, except one thing was different. I want to like substitute that in, kind of like a parameter to a function, but it's a textual substitution. That's a macro. And so we have those in assembly language, and then we also have them in C with the preprocessor, right? So once again, this is a textual substitution, happens before the compiler ever sees the C code. And it simply says, I'm defining this thing called IDX. It has 3 parameters. And when I use it, whatever the things is I give you for these parameters, I want you to substitute them in for what I put in this position, what I put in this position, what I put in this position, and spit out this code here, plugging those things in, right? So whenever it says IDX NIJ, it's just stuffing in this I times N plus J thing. Well, what is that? That's computing how we compute the index into an array, treating the two-dimensional array as if it was a one-dimensional array and computing how many bytes to hop over based on the row index and how many bytes to hop over based on the column index, right? We get the scaling of 4 happening because it's an array of integers. We're treating A like it's an array of integers. You pass in a pointer, an address of a two-dimensional array, and now in here, I'm internally treating it like it's a one-dimensional array and just rolling my own subscript instead of letting the compiler compute that formula for the index of a two-dimensional array. So that's how we used to have to do code that could handle any size two-dimensional array you wanted to hand me. We just do it in this kind of a thing, right? Where you manually do it with this macro. But this happens as a textual substitution at compile time, right? That would work, right? And we'd essentially get the same kind of code that we get out of this, but it was before we were able to use this n that was also a parameter to declare another parameter. So you may run into this kind of code. Macros in general by non-novice C programmers are used quite extensively. It can reduce the amount of code you have to type in significantly if you concoct a bunch of these little macros that are textual, parameterized textual substitutions in your code for plugging things in. So macros are used a lot in the standard library code and in any kind of sophisticated non-beginner type of C code that you might run into. You will run into a lot of these macros, and you can even have macros that use other macros inside of those macros. And so you can get really elaborate and complicated with these macros and these preprocessor substitutions. So hopefully you see the difference between what the compiler can do when it has the fixed size stuff and when it has the variable size stuff. Something's going to have to get computed at execution time that we could do at compile time up here if it was a fixed size thing. And hopefully these two different techniques for achieving the same thing make sense to you. Any questions about any of this fine points about passing arrays in as parameters and dealing with them, having fixed and variable sized arrays that we can deal with and how we deal with them. So that concludes the loose ends from chapter 3. Chapter 4, which we dive into next time, is on learning how to do some optimizations in the way that you write your code so that your code runs fast, right? It's a very crucial thing to understand how the code maps onto the computer and how the architecture of the computer actually operates, to know how to utilize it so that you can make it run fast versus some naive code that would be very, very slow. You can't see the question is about seeing the exams, and I take that that means, do you want to see the questions again and all that? No, you can never see it after you close that browser. It's gone forever. Because, um, I mean, I don't want to be insulting about this, but just the nature of the way people are in the current world, if I did that after I gave that test one time, it would show up on 27 different places on the internet for people to download and look at. That's the answer to that question. It's unfortunate that that's the world we live in, but that is the actual world we live in. So if I gave you the ability to go out and just look at that endlessly, that exam would be completely worthless other than using one time, because it would be stuffed out onto the internet by people, and people would do that. So it's a result of the fact that people are like that, that I can't let you do that. They don't post the SAT out there for you to look at after you take it, right? They don't want to have to make a new SAT test every month. Any other questions? All right. So I have office hours at 2 today. Your lab today is sort of some optional stuff of if you want to learn more about using VI and Emacs, if you don't need more skills in doing that, or maybe you want to do that at another time, you can use your time in the labs this week to ask your TA for guidance in your project that you're working on. If you think that would be more effective use of your time. So however you want to do that is up to you. And so if I don't see you at 2, I will see you Wednesday. Have a homework set due Friday, so look at that. All of these little examples that we've been going through here are available to you on the Canvas pages. I've got them all out there, and got the assembly language coded in 2 different ways, with the optimizer off and the optimizer on. So if you go to the week 6 stuff, you'll see in there this thing that says fixed and variable size or all that code is out there if you want to play with it and look at the assembly language that comes out of the compiler and compare it what it says in the slides or whatever. 2 problems in the 6 homework 6, and this is where we'll start lecture 16 Wednesday. Okay. If there are no more questions, I will see you either at 2 or Wednesday.